So this recently came out. It is an article that was published in Scientific Reports for Nature, and it is titled About Feasibility of SpaceX's Human Exploration Mars Mission Scenario Starship. Quite a long title. So yeah, the key takeaway from this chat is take it all with a grain of salt. Why? Because like I said earlier, this is talking about essentially the current understanding of Starship, and keep in mind that Starship's design is fluid, and there's also really no published numbers other than what we get from word of mouth from Elon and a few things here and there that Starship or that SpaceX publishes, but there's really no like full specification of what Starship is capable of. We don't get really any sort of dry mass, we barely have any sort of wet mass numbers, we don't really have a pinned understanding of its payload capacity right now other than what's in the Starship user's guide, which is like now like 2 or 3 years old. Yeah, there's a lot, right? The vehicle's design is fluid, and also keep in mind that this was just released, right? And it was probably written over the past year, doing all the analysis and everything. So they haven't even seen like IFT or Flight Test 3, and they will not have seen Flight Test 4. So yeah, take it with a grain of salt. What you might be asking is, why would they even write this article? Well, it's because of two reasons. One, this is a feasibility study, right? It's taking a look at what we currently know about Starship and currently know about other systems that might be some sort of comparable analog to Starship, and trying to just understand, is what we currently know or understand of Starship even feasible for future Mars missions? Because, well, really, that's the first step to identify any sort of technological gaps. We have to understand what we don't have available to us. So Starship is the launch vehicle. It's supposed to get crew there, but how did the crew stay there? What did the crew need to get back? All of these have to be identified, even if we are much further out away from the landing than what Elon currently says. Another reason for writing this feasibility report is that they are analyzing what is currently the, let's call it the baseline design reference mission, which is supposed to launch in 2029. We're 5 years away from 2029, which means that we actually have to start preparing for this mission now for any sort of payloads, for any sort of infrastructure. Obviously, that's not happening. Most likely 2029 is not going to be a realistic Mars goal, but they're analyzing that capability to see just how far away is SpaceX from actually meeting that. So not only do they analyze the 2029 launch window we have with Mars, they also analyze the 2033 and 2033 launch window for Mars as well. You have to start this stuff early, because it's probably going to take 4 or 5 years to even get any sort of preparations underway. Whether or not SpaceX has the capability is irrelevant if we don't have anything else in place that can actually use that capability, right? Pretty interesting. I actually really liked it. It reads pretty well. I have numerous questions about some of their assumptions and things. We'll get into that. But overall, I thought it was pretty well written. All we have right now is Elon's word of mouth. Like, quite literally, like if you think I'm kidding, if you look at the references here, look at some of their primary references that they used. Everyday astronaut, Starbase tour and interview. Everyday astronaut, Starbase tour with Elon Musk, part 1. They actually used Everyday astronaut, Tim Dodds from Everyday Astronaut. They actually used his Elon Musk interviews that he did in order to fill in some gaps on where certain mass plays might come into play, what operations SpaceX is thinking of. So yeah, of course this is not going to be like, you know, like I said, take it at face value for what it is. But again, it's a feasibility analysis to even understand, with the current stated goals, are they feasible? But it's really interesting to see how they broke all this down. If anyone who's actually done an aerospace engineering course, or probably any engineering course, right? You do like a capstone or some sort of senior design. And typically, at least for like me, what I had to do for my senior design project was develop a asteroid redirect mission. This was before, you know, Cyrus Rex came back, and before I think Cyrus Rex had just launched, and that's why we did it, right? This goes really well into how to actually conduct a feasibility analysis and to conduct a senior design project. So I thought it was really interesting. So getting into it, what's interesting to note is that they looked at what could possibly be comparable to the Starship system for this mission class. They came up with Orion. They actually used the Orion capsule to figure out the percentage of some subsystem that the Orion capsule uses, and extrapolated that data to Starship. You might be thinking, well, Orion is like a tiny 24 metric ton capsule and Starship is a massive like 500 metric ton interplanetary transfer vehicle. Yes, but it could be argued that their mission profiles or their design mission profiles are similar, right? Orion is meant to go into deep space. Starship is meant to go into deep space. So for things like life support systems and for things like possibly power systems and other things like that, it could be argued that Orion is a fair analog for comparison to fill in some of those specification gaps. And so that's what they used. Now, one of the really interesting things that they noted that is a current massive technology gap, right, is life support systems. Life support systems and in situ resource utilization, or ISRU. Those things are two massive technology gaps. Why? Because currently, ECLIS for the ISS is not in its current state ready to go into like deep space for a system that's larger, that has a larger pressurized volume than the ISS. So that was definitely one thing, right? So life support systems capable of ensuring human survival for several years do not yet exist with sufficient reliability. So how do you, especially going into deep space, especially for a crew of more than like say 7 people going interplanetary? Yeah, a life support system doesn't exist, has not been tested for that. Same with in situ resource utilization. Something to supply missions with fuel, water, and oxygen on the Martian surface. Doesn't exist. And it's going to be necessary to do. Why? Because Starship as it stands right now has just enough Delta V and propellant to get to Mars and land once it's fully refueled in low Earth orbit. So what does that mean? It lands and you have no fuel. So what do you have to do? You have to mine and create fuel when you're on the Martian surface. So yeah, that's what in situ resource utilization is. Basically using the Martian soil, the water that's in the soil there, whether it's ice or whatnot, using any sort of oxygen that might be available as like CO2 and stripping oxygen off. Everything that has to be used to create fuel has to be done on Martian soil, right? One of the biggest reasons for conducting this report is that they wanted to investigate a 2029 mission opportunity, and this is what they say. The most recent information about a possible launch date for such a human exploration mission to Mars has been a tweet from 2022, which mentions that his plan, Elon Musk's plan, envisions such a human mission in 2029, according to this reference. So, as I noted, this is of course Elon time, but Elon time sets the basis for this study's timeline. And so again, that's another reason for conducting this feasibility study now, is that based on current understandings of the vehicle, if we're going to even remotely hit a 2029 launch time frame, we kind of have to know where we stand right now, right? So published mission scenarios for Starship rely heavily on refueling, including on the Martian surface using ISRU to supply the fuel needed to return flight to Earth. Reliance on such technology for the return flight mandates a significant reliability to avoid stranding the crew on Mars. Starship as it stands right now, at least as far as we know, just to even get any sort of payload to something beyond low Earth orbit, it requires refueling. And so its current understanding for how to get HLS from low Earth orbit all the way out to the moon and land on the moon requires like 15 refueling tanks, right? Is like the baseline number. So just to kind of put the whole reliability thing into perspective right now, I did a little bit of analysis. Again, take these numbers with a grain of salt. I use like things like Wikipedia and stuff, but the reliability issue, how many refueling missions are actually required and how many infrastructure building missions are required. Looking at Falcon 9 alone, its overall reliability, just straight up taking the number of failures, which is 2, with the total number of flights, which is like 347, 348, comes out to be 99.4% reliability. Now, that changes because now we rely on landings. Rely on them. We rely on landings, right? For Starship to be able to do massive in-flight refueling missions for the design reference mission for Mars, which I think is currently in this paper 4 missions to Mars. You need 2 unmanned starships to take all the infrastructure out, and then they also have 2 crewed missions. So that's 4 starships. And to get 4 starships in a matter of 730 days, you essentially have to launch once every week and a half. And so to launch every 1 week and a half, I think it's fair to say that we kind of rely on landing, right? So looking at the landings for Falcon 9 and their success, they have like 298 successful landings out of like 310 attempts. And so overall, that's 97.1% reliability in that phase. So combined total, that's a 96.5% reliability rating so chance of success for each mission. So going up, launching successfully, right? And coming back down and landing is a full 96.5% chance reliability. Former NASA administrator who did a reliability study like this for the number of refueling missions that are needed. And this is what he came up with, right? For a 99% reliability rating on your flight vehicle, if you have to do 15 in-flight refuels, you're at an 86% probability of a fully successful mission in your flight window. So that's 96.5, so 0.965 raised to, let's call it 15 flights, right? That's a 59% of reliability for the entire mission architecture. But it's just kind of interesting. Like, is that a fair assessment? I think it can be argued that it's a fair assessment for that. For establishing that sort of reliability rating. Again, remember, this was written probably like 2 or 3 years ago, probably 2 years ago, because it just got accepted for publishing this year, and it takes about a year, right? So this is at least a 2-year-old paper, and so they didn't even necessarily know about the whole refueling flight number that just recently came out last year. All right, so moving on. A mass budget. So this is actually where they start talking about how they did their study. So one of the things they had to do, right, is of course make assumptions, extrapolations, to be used to fill in the technical specification gaps. Okay, so some of the questions that they wanted to, of course, address with this feasibility study is: one, is the mass information provided by SpaceX plausible? It is not. Is the propellant mass given by SpaceX plausible for the given mission scenario? It is not. Is the time of flight aimed at by SpaceX plausible? It is not. What is the energy needed for ISRU activities on the Martian surface, and how can it be satisfied? So going back to it, essentially all of these questions boil down to: is Elon time and Elon hype reliable? The answer is no. Again, remember, take this all with a grain of salt. This is a 2-year-old article, so the numbers that they're working with is 2 years old. The numbers that we even have now are not really reliable, right? We don't have any working numbers from SpaceX other than certain things that Elon has given us tidbits in interviews and such. But yeah, essentially, when it comes to doing Mars, it is extremely difficult. And I think this paper breaks that down pretty significantly, which is really awesome. They actually explain in pretty good detail how they brought together all of this missing information and tried to set out, to some realism, to some confidence level, a mass budget breakdown for Starship. So first, a literature review was conducted to compile available data on Starship system mission design. They found information is filtered based on recency and reliability. The mass budget is set up using ESA's margin philosophy for feasibility studies of science missions. Specifically, this means that an overall 20% margin is assumed for the system mass. It's a very well-known and accepted practice that if you don't know specifically what your system's mass or performance in a certain area is going to be, you add a margin to it. You add some percentage, usually to worsen the scenario, right? So for instance, if SpaceX currently says that the system mass of Starship should be 100 metric tons, well, just to allow for that to change in the future, since it's still in development and it's not actually known, you add a margin, in this case 20%, which is pretty big. So that 100 metric tons becomes 120 metric tons, right? For the system mass. So you basically are providing a worst case scenario for what the end result will eventually be. So one of the questions I had is, how applicable is this? Why? Because Starship, if you really think about it, is not like any other launch vehicle ever previously devised. So that was one of the questions I had, something to keep in the back of your mind, that for some of these assumptions, where do the assumptions actually break down? They're using a template, if you will, on how to conduct the survey with unknowns involved, right? Other things they do is they add 5% for off-the-shelf items that are essentially unchanged. So margin covers only additional bolts, screws, and similar elements. 10% is added to be modified items. So items with heritage that are used as a baseline, but will maybe need some modifications to improve performance or to integrate it with the vehicle. So 10%, a minor margin to account for any sort of modifications to Starship or for Starship. And then finally, 20% is to be developed, completely new technologies, where all we have is some assumption on what its end mass is going to be. The estimate is probably going to be inaccurate, so let's definitely improve or increase a worst case scenario margin to our system. So the philosophy, so this particular design philosophy for margins was picked for reasons of familiarity by the authors. So I highlighted that just so that we all know and keep in mind that this doesn't, of course, reference any of SpaceX's design activities or the way that they conduct their design or the specification of Starship. It was just what is known to the authors and seems to be a pretty good starting point for any sort of mass analysis and system analysis. So they also talk about in this table a summary of numbers provided by SpaceX concerning its Starship mission scenario. So system mass, including the 20% margin, is 100 metric tons. They got that from source number 8, SpaceX Starship's User's Guide. So if we go to the Starship's User's Guide, it probably says that the Starship mass is around 100 metric tons. Remember, that's the system mass, that is not the payload mass. Are saying, okay, we're going to use their overall system mass that they tout, and we're going to say that that includes the 20% margin. We also have estimates for cryogenic methane storage on Starship, to other references, cryogenic methane storage for Super Heavy, propellant tank mass for Super Heavy, the payload mass, which is also from Payload User's Guide of 100 metric tons, and then of course what is perceived to be the perigee velocity on Mars and Earth landing. So one of the things I wanted to do here is just how do all these numbers fit into things, right? So Falcon 9, for comparison, its first stage is approximately 23 metric tons, and its upper stage is approximately 4 metric tons. For payload, which was really interesting, roughly the maximum payload of Falcon 9 in expendable mode is probably around 20 to 25 metric tons. And then this was interesting. I wanted to break this down into the propellant mass fraction. So for the first stage and the second stage, not including any sort of payload, the propellant mass fraction of Falcon 9 was 94.5%. So it's 94.5% propellant when it launches without payload, right? When you take all those same numbers and you break it down for Starship Super Heavy, the propellant mass fraction comes out to be 96.4%. That Starship should not be as optimized as Falcon 9. Why? Because unlike Falcon 9, it should have tiles, thermal protection system for reusability for landing. It, of course, is made out of stainless steel, a much heavier material than what Falcon 9 is made out of. It's got more engines, it's got more dry mass. It's not a one-to-one comparison, right? Like your propellant mass fraction doesn't just scale linearly. It all depends on the diameter of your system and the height of your system and how much propellant you can get into a volume. And volume, of course, doesn't scale linearly. Just an interesting comparison to see. So now we get into their rapport of Starship system and payload masses. Where no information was available to Starship, data was extrapolated from the existing systems based on Orion technology, the Orion capsule, the one that's being used for Artemis. Like I said, this was solely to be used for data gap filling. Of course, we always have to ask ourselves, how applicable is this? They do explain this to some degree about, of course, Orion is not a one-to-one analog of Starship. Nothing is a one-to-one analog of Starship, right? But also remember, in terms of mission class, Orion is currently the only vehicle that we have in development and arguably operation that does a similar mission class, which is deep space missions. Orion was actually designed to go into deep space and to take astronauts to Mars and to take astronauts to Venus and so on and so forth. Then you have to think like, okay, but where does that analogy break down, right? Because Orion is like 23 metric tons and Starship is like 1,300 metric tons, right? When it's all fully fueled. Let's get into the trajectory analysis here. So the first thing that they talk about is trying to match the known trajectory with SpaceX's time of flight desires. So what does that mean? So SpaceX has published that they desire flight times to and from Mars on the order of 80 days and even 30 days, a 1-month trip to Mars. You can only do that with a lot of Delta V, like a lot of Delta V. Typical time of flight for Mars is like on the order of like 100 days. Or maybe even like 200 days, depending on really how much Delta V you have at your expense, right? In general, the trajectory analysis of an interplanetary mission was broken down to the problem given departure and arrival position vectors. This is using a Lambert solver based on an algorithm developed by Batten and Vaughn, and it was implemented in MATLAB according to the pseudocode provided in Volato and McLean. It uses the position vectors of Earth and Mars. The position vectors are modeled with the mean orbital elements. So a few things to take away from here, right? This is, so the Lambert solver is a very, 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 very well-known and highly or widely used system for solving trajectories in orbits, right? Whether they're interplanetary or just, around the moon, around Earth, whatever it have you, Lambert is a very useful method for figuring out your trajectory. But there are things to understand here. Typically, depending on the exact implementation here, Lamberts are only using the two-body assumption. So you're not getting in-body effects, you're not getting the effects on perturbations from your orbit, you're not getting any sort of like solar radiation pressure perturbations, gravitational perturbations. Not only that, but also depending on the implementation, you're also doing impulsive burns, which we all know is not possible because we do not have an infinite amount of thrust to just be able to instantaneously change our velocity. So yeah, nothing about that is really out of the ordinary. Just keep in mind that, of course, it is using assumptions. Okay, so the Lambert solver then returns the delta V values for the necessary maneuvers at Earth and Mars to connect the two planets with an elliptical transfer trajectory. This does not account for the influence of Earth and Mars gravitation on Starship. Therefore, the values are adapted with the use of patched conics. Since SpaceX plans to refuel Starships in LEO, the orbital altitude must be chosen high enough to not deorbit due to the atmospheric drag. An orbital radius with an altitude of 500 kilometers has thus been selected. So then they go through and talk about all the different velocities on how to figure out the delta V, right? So one of the things they said was, one of the interesting things that they did was looking at how much correction delta V is required for the in-flight corrections. So they actually went to the Pathfinder mission. So Pathfinder had, for its corrections, a delta V requiring of around 33 meters per second. But what we also have to remember, right, is that Starship has to have a very accurate landing. Why? Because in terms of their design reference mission, they require all 4 starships to land basically next to each other. Why? Because you're using in situ resource utilization to produce propellant, and that propellant has to be transferred to the other vehicles for flight. So what does that mean? You basically have to land all 4 starships within some sort of very low vicinity, very tight vicinity, to minimize the amount of piping and propellant infrastructure you need just to refuel your starship. So yeah, with that assumption, they increase the delta V margins for corrections up to 200 meters per second. They define the amount of delta V for Mars insertion. They also define the delta V required for landing. So they do the landing delta V, and then on top of that, of course, they, according to ESA standards, they put a 5% margin to get their total delta V to go from Earth to Mars. For their trajectory analysis, and this was one of the things that I was like, does that really make sense? Is they wanted to figure out, based on the amount of delta V that the mission required to go from Earth to Mars and Mars back to Earth, if it doesn't require a full sort of tank of gas, if you will, could they then exchange that propellant that isn't needed for payload mass? And I thought to myself, I don't think that's really, I've never heard of that actually being a case for a vehicle where, like something like Starship, right, which should be more or less standardized and has like this much payload mass, that you would somehow change the design of Starship to account for more payload mass, and because you would fill it up less with like less propellant because you don't need it. Like that has been done to like some launch vehicles in order to, you would change your propellant mass if you're, launching a lighter payload. You have a maximum payload mass and that's it. That's what you're rated for. So they talk about the ascent data is not from SpaceX. So we decided to collect data from different sources and studies and extrapolated values for Starship from this data set. Why? Because SpaceX does not disclose any information regarding a low Mars orbit ascent and the delta V required. So we assume that Starship will ascend into a 250 kilometer circular altitude. This orbit around Mars has a velocity requirement of 3,430 meters per second. During the ascent, Starship is expected to have losses that decelerate its movement and need to be overcome by further delta V. So they're explaining how they came up with this number for getting into low Mars orbit. So just generically 250 kilometer altitude should be sufficient. That's, you know, kind of like a 500 kilometer circular altitude around Earth. Going to that requires delta V of 3,430 meters per second by itself. Now we also have atmospheric losses and gravitational losses that we have to apply. So how do they do that? It's all based on the thrust to weight ratio. Why? Because if you have a lower thrust to weight ratio, you're going to have more gravitational losses. Right now with the aerodynamics are luckily at least play a slightly less important role here, because Mars's atmosphere is like 2% the atmospheric density than on Earth. So your atmospheric losses should be way less, but they are also something still to consider. So what they were able to do here, chat, is get an estimate for the thrust to weight ratio of Starship. So on the Martian surface, we should have a thrust to weight ratio of 2.819. A typical thrust to weight ratio here on Earth is like 1.2 to like 1.5. I think the space shuttle sometimes took off with like 1.6, and that's really fast. So yeah, 2.8, huge, but also keep in mind that's in Martian gravity, but still. So not only that, they also looked at the Mars Ascent Vehicle. They looked at studies for the Mars Ascent Vehicle, which I thought was actually really cool. So this little guy, right? This little guy. For the Mars Sample and Return mission, the Mars Ascent Vehicle, they actually looked at, again, because this is like the closest thing we actually have to a known to a known mission that is in current design development for Martian atmospheric takeoff into a low Mars orbit. This is like the closest analog we actually have, and took all these studies that were looking at thrust to weight ratios and atmospheric losses and things like that, and gravitational losses, and created an analytical solution here for that could be used to estimate. And so therefore the delta V for the losses of a Starship can be assumed to be 1,352 meters per second. This allows us to directly express the needed delta V to reach into low Mars orbit. So based on the thrust to weight ratio, and based on these studies here that they all list that you can go look up yourself, they took that to be the losses required for Starship. So from that, we get the total delta V required just to get off the surface of Mars into low Mars orbit, that low Mars orbit being 250 kilometers circular. So yeah, that is the total delta V, including all of the losses. So putting that all together, putting it back into the equation that they had here for all systems. So this is the amount for landing, delta V from escape from Earth, delta V for Mars insertion, the delta V for ascent back into low Mars orbits, and then finally the amount for corrections. And then on top of that, a 5% margin. All of that gives us the amount for our, the amount of delta V that we have at our expense. Now we look at another fun system to start bringing into the conversation, which is the ISRU. Based on current known technologies, how big of a system do we need in order to develop 2,400 metric tons of propellant from the Martian surface? You might be asking, why 2,400? Because the design reference mission is 2 starships landing crew, which means we have to bring back 2 starships with crew. At least that's the design reference mission that they're going for, right? That I think they took the design reference mission from SpaceX. Yeah, so they wanted to understand, review the state of the art of the systems as a data basis, extrapolating mass and power for an IRU system, mass and power for the Martian system, and then of course extrapolating mass for the transportation of the systems. Yeah, so they want to understand current tech and basically extrapolate what SpaceX needs for the design reference mission. Let's get into the baseline mission scenario. For our purpose, we assume 2 crewed missions carrying equipment for power generation and ISRU will launch from Earth in 2027, and 2 uncrewed and 2 crewed starships will travel to Mars in 2029. This, at least for the design reference mission, is 4 starships total. As I said, with the current baseline estimate for the number of refueling starships we need to refuel each one before they go to Mars, that is 60 starship refuelers, assuming 15 each. That gives us roughly a 70% probability of success. When we use Falcon 9's rate of success, 99.7, is Starship going to be able to have a better rate of success? Hopefully. But even using Falcon 9's very, very high rate of success of 99.7, just using a simple first order approximation for reliability on all of those missions comes out to be 70% to hit our desired timeline of 2029. Just something, like I said, keep in the back of your mind all the refueling that has to happen in between, right? It's not just for starships. So as a baseline, the crewed version is assumed to carry 12 persons, but it will also be reviewed for the effect of carrying 100 persons. These assumptions are time of flight of 180 days for flight to Mars and back to Earth, as well as 500 days of surface time. So you might be asking, why 180 days? Well, because that's literally like the lowest that they could achieve, because SpaceX wanted 80 days. All right, so let's get into the Starship system mass. So it says Starship can carry a payload mass of 100 metric tons according to the Payload User's Guide. SpaceX targets a system dry mass of 100 metric tons. Assuming a 20% system margin, and according to ESA's design standards, this means that there are 83.333, repeating of course, metric tons of mass available for actual subsystems. So basically they're saying, assuming a 20% margin that the system will grow because it's unknown, then the current known mass of all subsystems on Starship, excluding payload, should only account for 83 metric tons. SpaceX gives the propellant mass as 1,200 metric tons on their website. Being the most recent number, this is taken as baseline. Now, because of this, to account for boil off and propellant going to gas, which is technically unusable for your maneuvers, they assume 2%. 2% is unusable. So that gives a total usable propellant mass of 1,176 metric tons. They're really going through and thinking of a lot of different ways that there could be losses. Again, this is kind of like a worst case scenario, also trying to be a realistic scenario for Starship's current design. So let's get into the mass budgets chat. So this is where they break down and try to assess the entire mass of Starship component for component, or I should say probably more accurately, subsystem to subsystem. So first and foremost is protection. The importance of crew, sleeping compartments, and control center leads to the assumption of a polyethylene cover. Furthermore, it is assumed that water pipes cover as much habitable volume as possible to minimize necessary mass on board. Equipment and cargo, food are also used for radiation protection. So polyethylene is part of the protection for radiation. Habitable volume of Orion is around 3 meters cubed with a total pressurized volume of 20. For Starship's first missions with a crew of 12, 16% reduction for elements not scaling linearly are assumed, 10 times the volume of Orion for larger cabins and rooms. Thus, for model, approximately 90 meters cubed are habitable and 200 meters total pressurized. Absolutely massive, chat. Going from 9 to 90, 10 times is their estimate. And that's actually on the lower end of what Starship could actually achieve as a habitable volume. They account for 30 metric tons of shielding. They also go into the minimum requirements to keep the crew happy for long duration missions. So the needed crew room set to a marginal minimum. So from other papers they actually used as part of the study, they basically have a ratio of like how much room do astronauts need for longer and longer missions. For example, for a 3-month mission, the optimum is about 15.5 meters cubed, with a minimum of about 7 meters cubed. And so they took that and they said that for the long 180-day mission that Starship will do, they will require anywhere between 135.6 meters cubed and 240 meters cubed. So the assumed 90 meters cubed of this paper, thus on the lower range, and from a mass budget point of view on the optimistic side. So they actually tried to be a little optimistic here on how much pressurized volume the crew actually needs. Yeah. So they also talk about protection from micrometeoroids. So that's 22.1 metric tons of protection needed for micrometeoroids. So then we get into how much structure is needed to just support 100 metric tons. So for that, they say the results in a mass of 37 metric tons for additional structural mass to hold up that 47 metric, or to hold up that 100 metric tons of payload. So yeah, this is what a Whipple shield is. So this is their concept of a Whipple shield for Starship with 2 bumper shields and 1 back wall. So essentially you have a aluminum shell here, and then you go into Kevlar, right? And then you also have perhaps a back shell. But does that mean that it's going to need all 4 of these layers and then stainless steel? That's my question as well. So the result for just the structural mass is 40.7 metric tons, according to the stainless steel required from the outer skin with that density in order to hold up 100 metric tons on top of it. All right, mass of the thermal protection system. I thought this was awesome because we've been wondering for a long time, right? Like, how much does the tiles on Starship actually weigh? And so they estimated here, right? Again, take it with a grain of salt. But they talked about pica X, and with the surface area, assuming a cylinder, which is of course not a cylinder, with a 6 centimeter pica X heat shield, would require 22 metric tons of thermal protection. Assuming not every part needs to be covered with the full 6 centimeters, but on average 3 centimeters would result in 11 metric tons for the heat shield. Now, the other thing I was actually questioning here is we all know that Starship is not fully covered, right? Not all the way around it. It doesn't need it on the top, for instance. So at that point, possibly it would be more like 11 metric tons, right? 6 centimeter pica X, but only on like the half of Starship. So I'm wondering if that was something that actually should be taken into account. Getting into ECLS, right? It scales with the CO2 output. So it scales with the number of astronauts that are living in the pressurized volume of Starship or whatever vehicle that you're operating. They actually took Orion numbers. So Orion has a mass of 1.2 metric tons for its ECLS system. And so Orion is also only designed for up to 4 crew member. So when you scale that up to now a crew member of 12, you have 3.6 metric tons. 12-person crew instead of 4. Good insulation is provided by 40 layers of MLI with the surface density requiring 2.21 metric tons. Now, this is another question I had. Is MLI necessary given that 304 stainless reflectivity and the use of black tiles? With the reflectivity of stainless steel to be able to provide a surface that will reflect heat, you could also do what with the tiles that are now black on the bottom. If you actually need to increase the heat in the system, you could actually rotate your tiles, the black tiles, towards the sun to absorb it. So I'm wondering if the MLI, especially 2.21 metric tons of it, is actually necessary here. Okay, for the comms and avionics, I took it straight from Orion because Orion's comms are meant for deep space. So we know the mass of Orion's comms. Let's just put it in and use it as an estimate for Starship. So 0.6 metric tons for comms. So going into the amount of power that Starship will need and how to size its solar arrays. So they actually went with Northrop Grumman's Megaflex system. And so they were talking about having these massive ones as a baseline, again, for power output, size, and mass, but for Starship. So I thought that was actually pretty interesting. So they actually go with this for the analog. But anyways, for Starship to actually function with 12 crew members for 180 days, all the way out to Mars. Keep in mind, when you go out to Mars, the amount of solar energy that your solar panels can effectively use decreases because you're going further away. So not only do you need 100 kilowatts, so 100,000 watts just to power Starship for 12 crew members, you also have to account for the amount of radiation intensity decreasing by about half during the flight to Mars. So what does that mean? You got to kind of double it. So they're saying that you need an output of around 250 kilowatts just to power Starship once it gets out to Mars. It's 250 kilowatts from like Earth perspective. It's rated for 250 kilowatts. So altogether, you need a diameter of around 24 meters. Together, the two arrays have a mass around 2 metric tons. To add this to 5% margin, so yeah, you get 2 and some change. One of the things that I had a question of is ROSA, the rollout solar arrays. They're now on the ISS. Because one of the things that they actually talked about, the reason why they went with Megaflex arrays, right, is that the solar arrays, if you're landing your system on the Martian surface, have to be retractable. And typically, most solar arrays are not retractable. Like all the ones in typical configurations for spacecraft, for satellites, right, they're not retractable. But ROSA is, and then also, of course, the Northrop Grumman Cygnus style of solar arrays are retractable, or at least can be made retractable. But I thought, why didn't they go with ROSA? But probably because it's not really a proven tech, and of course the Megaflex has flown on Cygnus and has flown on Insight and things like that. But it was interesting. I thought this was also awesome. They use Tesla batteries as their baseline in order to be able to function for 12 crew members in the event that you go behind something like Mars during your descent. So they use Tesla with their 100 kilowatt hour batteries, requiring a total battery size of 6 kilowatts for 6 hours of assumed battery life. So all of that together, each Tesla battery, 100 kilowatt hour battery, has 625 kilograms, and a factor of 1.2 for aging and recharging results in 9 metric tons for all batteries in total. Here we also increase a 5% margin, which brings the entire EPS system to 12 metric tons. All right, propulsion system. Propulsion system, pretty straightforward. Mass of Raptor, mass of propellant, and the required tank volume and the mass of stainless steel. They go through all of that, bringing the entire tank mass for Starship to be 20.3 metric tons. And then they also included pressurization tanks like helium for cold gas thrusters and assumed that to be 5 metric tons. And then on top of that, they assumed that there would be probably around 50 RCS thrusters, because something the size of the space shuttle had 44, so 50 RCS thrusters, each approximately 2 kilograms, therefore 100 kilograms, bringing the entire total of 5.5 metric tons for RCS control, all of that jazz. So we also have our propulsion system, our tank system, and I think they also mentioned the mass of 6 Raptor engines, which is 12 metric tons. So covered all of our bases, propulsion as well. Now finally we get into something a little bit more nuanced, which is the crew consumables. And of course there are no details from SpaceX regarding how much consumables 12 crew members need, and therefore that we don't really know the sizing of Eclipse, but we can at least estimate from Orion, and we already did that, right? But they assumed for their baseline a best case rate of 100% recovery for gases, fluids, and solids. So what does that mean? Basically, they are assuming that the Eclipse system can provide everything for the crew members without any sort of resupply. So bringing it all in total regarding, a recovery rate of 100% means that in theory, the systems are able to use an initial payload mass required for 12 astronauts for 1 day and completely recover it. Therefore, the system is, by calculation, able to supply the crew without any additional storage or resupply for the entire mission. So again, that's kind of a best case, right? Because in reality, you're not going to recover food. You know what 100% recovery of food means? Anyways, hygiene items and clothing should be 0% recovery, right? Now for water and potable water and stuff like that, yes, we can recycle that. Oxygen we can recycle. But yeah, they went with the best rate of 100% recovery. So in summary, with the bottom-up estimates as formulated in the previous sections, a mass budget summary can be formulated. This is shown in table 8. We'll get to that in a second. The total on-orbit mass adds up to 1,510 metric tons, of which 1,200 metric tons are propellant. Now this is a problem, chat, because we also have 100 metric tons to payload, and the consumables, including for 12-person crew. This is assuming that 100% of the consumables can be recycled by the Eclipse. Overall, the total mass on orbit is exceeding the proposed mass summary by SpaceX by more than 100 metric tons. This is summarized in table 9. I kind of brought it up here. Would astronaut resources not trade with payload mass? That's something I think we can all agree on, right? Why is there 100 metric tons of payload? Where is that stored when we have a pressurized volume and all of the consumables and everything needed for astronauts? Not to mention, in most cases, I don't think I've ever heard of a launch vehicle being constrained by mass before volume, right? Like, think about it. Like, what are you launching in the volume of Starship that's getting you 100 metric tons inside of that volume of Starship? Moving right along, chat. So they go into the trajectory analysis. They basically give the statement for the total days. It's an 860-day mission. So that's 180 days outbound, 500 days on the surface, and 180 days inbound back to Earth. I went through this table and really tried to figure it out. So first and foremost, like I said, I wanted to look at it to try and be a little bit more reasonable with what I understood, right? But anyway, so getting rid of that, we bring it down to 161.1 metric tons, which should be the correct calculation here. But here's the thing. If we get rid of the 100 metric tons of payload, that brings us much more in line with what should be the case for Starship with crew, in my opinion. If you bring everything in full, right, the total dry mass of Starship, according to their numbers, right, is around 204 metric tons, which is still way over the target goal of SpaceX being 100 metric tons, right? SpaceX says the dry mass of Starship is 100 metric tons. But going through subsystem by subsystem, they've estimated it that is basically 204 metric tons, right? Huge disconnect no matter what you do, is the delta V numbers, right? So with everything here, with the 100 metric tons of payload, with the astronauts and all of that sort of stuff, we get a delta V of 5,588. Now remember, that payload mass does come back for the uncrewed flights. So the uncrewed flight systems would probably have around that much, unless we can figure out a better way to get Starship's mass under, which if we can rearrange some of the meteorite shielding, maybe less of it is needed and all that, or maybe the heat shield isn't needed as much, or the MLI isn't needed, then we can actually get that down to around 170 metric tons, all things included, and have a payload mass available of 27.7 metric tons, including the astronauts. There's some mixing and matching going on here, right? But yeah, it still doesn't look great for Starship, no matter what. But then they also talk about the tank losses, right? Remember, 2% of the propellant cannot be used, and we also lose propellant during the in-flight corrections and all that sort of stuff. So in reality, we actually have a little bit less delta V than the 5,864 meters per second due to that imperfect losses of 275, boil off and what have you, right? In general, a transfer becomes feasible every 22 months, an event that is called launch opportunity. Such launch opportunities stay open for 45 to 160 days in the case of Starship. Keep in mind refueling. So at what point is Starship going to be able to hit that? Yes, SpaceX is arguably operating faster than what they were with Falcon 9. It probably won't take them necessarily 10 years once Starship gets operational, but what does that look like? Remember, this is for a flight in 2029 for Mars, because that's what Elon was originally saying. Take that with a grain of salt, Elon time. But that is what we're going with in terms of our baseline. Looking at feasibility for a 2029 flight. And so if we think about it, for 730 days, that's what 22 months is. If we assume we start at the, after the 2027 mission goes, we can of course start earlier, but also Starship. If we start earlier, that means Starship has to be ready earlier. So let's just assume that we start the refueling missions after 2027, after the ISRU cargo missions go. We have 730 days for 64 flights. That would require one flight every 11 days. We talked about that already, but still, that's huge, right? So what's interesting is that they looked at two flight windows. First one they looked at was 2028 to 2029, and then the second one they looked at from 2033 to 2035. And this is what we get. This is 2029. From SpaceX's calculated margins on their delta V, they have one launch opportunity. Now again, remember the probability of hitting your launch window requiring 60 some odd flights for refueling and everything, right? That brings it down to like 60% if we assume 99.4% reliability, I think, in all systems. So we have a 70% chance of hitting our flight margin on this 1 day window that hits us our best margins for the flight opportunity. 2033 has many more flight opportunities, way less delta V requirements to actually get there and to land. 2033 looks way more feasible. So 2033 looks way more feasible just from a trajectory analysis, just from understanding what the current mass budget is for Starship and what is likely feasible at this point. 2033 is the goal. So this is what I was talking about earlier, but what happens if their system mass is not the system mass that they estimate? So they did a sensitivity analysis to see how much delta V Starship would actually have. with different system masses. So with the current assumption of 210 metric tons, we get the 5,588. If they're able to bring that into 150 metric tons, we get almost 6,200 meters per second of delta V. So many more flight opportunities, much better margins, all that jazz. All right, so feasibility of return flights. They assumed, of course, that no payload apart from the astronauts and consumables are returning to Earth. That, of course, probably won't be the case because we'll probably be returning like Mars samples, but how much Mars samples? So the maximum delta V for the return flight is 6,651 meters per second. It has been shown that the ascent to LMO alone consumes 4,782 meters per second, which is 72% of the delta V budget, another 6% used for TCM. So that leaves a budget 1,330 meters per second, or 20% of the maximum allotted payload for the two remaining maneuvers, which is Earth insertion and then of course landing, or sorry, Mars departure and of course landing. So they go through, we all know Starship is landing with like 0 propellant left. It takes like 5,500 meters per second, or maybe so at best it takes like 5,000 meters per second to get from Earth, low Earth orbit, refueled all the way out to Mars and landed. 5,000 meters per second delta V. Starship, with its current estimates of mass that they use, requires or only has around 5,500 meters per second of delta V. So there are some margins, but they're basically landing on empty, right? So we all know that to get the crew back, we're going to have to use in situ resource utilization, or we have to refuel them with more cargo. So they actually go through and try to figure out, based on current ISRU technology, which is pretty much only lab demonstrations at this point, what systems would we need in order to get the propellant sufficient enough to actually fill up a Starship. So what was interesting is that they looked at current ISRU technology. The current one that they have is that they looked at with this study is 2 kilograms per day with a system mass of 75 kilograms and 1 kilowatt of power requirement. You know, we're basically having a 30-day buffer with 500 days for the duration of the mission, which gives us a total of 470 days to refuel Starship. So that means that we have to achieve 5 metric tons of propellant a day, which requires 2.55 megawatts of power. That results in a mass of 191 metric tons. So just for the ISRU system, we need 2 Starships. So 510 kilowatts are added, giving a total mass of the system of 230 metric tons for all ISRU materials, and an average power demand of 306 megawatts for the power system. Both are adding a 10% to be modified element, resulting in a total of 253 metric tons and 3.37 megawatts of average power demand. So right now we need now 3 Starships. To prevent the pipes from becoming too long and to keep the distances as short as possible, Starship must land close to each other. That's what I was saying earlier. So there's a risk of proximity happening here as well. But you need at least the 3 ISRU ships now and the 2 crew Starships to land in close proximity. So you need 5 in a pretty tight cluster. Does this assume that it has to cover nighttime to solar requiring battery? Yep, it does not actually. Remember, they baseline the power system 6 hours, and I think isn't a Mars day like 23 hours or something like that? Isn't it close to Earth hours? So half of that should be night. So yeah, you need like double that. So yeah, their power system is actually not even sufficient enough. But how long is it going to take for them to set up the ISRU system? If you only have 6 hours of battery life, I would assume you need power during the whole period, right? Like, is the ISRU system going to be immediately accessible? How long does it take to set it up? Is it, you know, like that's something to think about. Yes, here we go, chap. So, of course, to achieve that 3 megawatts of power requirement with margins, they're going to, the paper here proposes a larger version of the scalable fission surface power system, which are 2 nuclear reactors. So yeah, they need 2 megawatt nuclear reactors in order to fulfill the entire power consumption requirements of the ISRU systems and Starship. This results in a mass for the PSS, for the power system, of 64 metric tons, with each nuclear power system being 32 metric tons. The total mass of the surface systems is 328 metric tons. To ensure the propellant production for the case of 1,200 metric tons propellant for 2 Starships. Remember, there's 2 cruise ships that have to come back. there is a lot involved with this. So it's kind of crazy to think about all of the technology gaps. That's the whole point of a feasibility study, right? Is to see what's feasible now and what do we need in order to make it feasible if it's not feasible right now. About in this case, they talked about the dissimilarities in Orion and Starship in terms of like the mass, right? Because Orion's structure mass is considerably lower than Starship, but also Starship is using stainless steel, so perhaps that's a reason for it. But they're all, you know, they're talking about why would that discrepancy be there? Especially what would be included as protection and other, like for hatches and cabling and docking and all that sort of other stuff. So they do a good discussion on what might there be room for improvement here for the mass budget. Of course, they go back to saying that we are at a best case of 100% recovery rate, where in reality we're not getting our food back. We're not recovering our food. I don't want that. No, thank you. So yeah, you're not getting all of it back, but you can definitely get a high amount back, but 100% is not the case, right? Let's see, what else do they talk about? Especially for early crewed missions to the Red Planet, this option serves as a relevant safety option. They're talking about free return trajectories, chat. Especially with, free return trajectories offer the opportunity to remain on the elliptical transfer orbit for a duration of a maximum of 3 years and return to Earth without the need for additional maneuvers. It is stated by SpaceX that Starship will be able to transport 100 astronauts, so that also has to be taken into account. We're only assuming 12 here. That's pretty much it, chat. But technology readiness, the radiation and micrometer protection, as well as the components for ECLS comms and corrections, are technologies that have already been used on previous spacecraft for a high degree of technology readiness. The Megaflex solar arrays for the EPS are based on the Ultraflex, which has a flight heritage and TRL 9, so technology readiness. A Megaflex array of 9.6 meters has already been tested of a TRL 5 demonstration. So those could be operational by the planned launch date of 2029, probably if they start now. The next new technology to be considered are Starship's main engines, the Raptor engines. At the time of writing, they have not yet been used in space. Well, that's changed now, so that's good. But will be from 2023 onwards, and that is true, during the orbital flight tests. However, they have already been used in numerous tests on Earth, so their level of technology readiness is medium, approximately 6. For the RCS thrusters, those should all be readily doable. But yeah, so talking about technology to produce liquid methane and oxygen would work on Mars has already been demonstrated with Imisips. However, this system has only a fraction of the propellant production rate needed to fuel two starships. In addition, such a system without water extraction plant requires 2.55 megawatts of power, even with assumptions of technological readiness that have been made. Therefore, it is seen as critical that such a system is operational and flight ready by 2029. So yeah, there's one of your critical technology gaps. The technology readiness for the fission surface power system is also not yet very advanced. Technology demonstrations has already taken place successfully on Earth with a smaller 1 kilowatt reactor. Remember, we need 4 megawatts. This is 1 kilowatt. The problem with the FSP, however, is the estimated time to operational capability. Systems with 10 to 20 kilowatts are expected to be flight ready in 3 to 5 years. The required 2,000 kilowatt systems are probably in 10 years. So yeah, overall feasibility has been shown that the current available information extrapolation does not lead to a feasible mission scenario for SpaceX. So recommendations. It has been shown that the current plans for Starship missions and their feasibility show significant gaps. For closing these gaps and improving feasibility, the following recommendations are made. Aim for uncrewed Mars missions to improve mission reliability and heritage. Include more international partners, possibly political organizations, to enhance the necessary technology in ISRU, power generation, and ECLS. The scenario analyzed in depth here has shown that a high recovery rate of consumables is relevant to reduce the mass, and even with 100% recovery at the moment, the mass is not fitting the mission requirements. Therefore, developing life support systems with a large recovery rate is mandatory to not further increase the gap between performance and actual mass. But that's also, again, assuming that Starship's mass is what they say it is, which is, with their estimations with 100 metric tons of payload, is negative by 100 metric tons. So just not have any payload and you're fine. Possibly use one-way cargo versions of Starship to reduce the amount of propellant that has to be created in situ, and use them as stationary elements instead of infrastructure elements, which has to be transported along with the crewed starships for habitation or reusing Starship solar panels. Yeah, like I said, if you're asking yourself why are they even doing this, well, it's because this is just a feasibility study, because now is the time to start at least thinking about what could be possible for a Mars mission, especially when Elon have come out saying that they want to do a 2029 mission to Mars. That's what this is. They're just saying, hey, these people are saying they want to do this. Is it possible? No, it's not. Not with the current state of everything. The first stage you do with any sort of mission is a feasibility study. Why? Because you have to identify the technology gaps, because you have to start filling those gaps, right? If you want to do any Mars mission for even the next 20 years, whether with Starship or not, you still have to have some of the same technology. ISRU could be helpful. Higher recovery rate ECLIS. There's so much. Power systems, right? Solar arrays, roll out solar arrays and stuff like that. Like, all of that stuff has to be figured out and identified now. So yeah, that would be the reason why this paper is coming out. And also remember, take it with a grain of salt. It's 2 years old at least, so they haven't seen even some of the most recent tests. And of course, Starship and Super Heavy are in very fluid design, so the numbers they're working with are the best anybody can do.